All right, we're going to get started. So let's settle in. All right, so we have, today we're going to continue on with Chapter 9 material. So the homework assignment this week, I believe, is still Chapter 8, second part of it. So we're a little bit ahead now, finally. And I think there's also 2 Chapter 9 assignments. So the stuff we covered today, I forgot to check the exact cutoff, but in terms of the material for Exam 3, I think everything that's on there we're going to probably finish today. So there's basically there's 3 parts to Chapter 9, depending how you divide it up. We covered liquids and intermolecular forces on Tuesday. Today we're going to cover phase changes mainly, and those topics will both be on the 3rd midterm exam. And then the 2 lectures we do next week, which are going to be on solids and crystal structures and things, that, as far as I know, is only on the final. I'll double check that and make sure you're clear on that before, and you'll see the exam review exactly where it cuts off as well. So only part of Chapter 9 is going to be covered in the 3rd midterm exam. That's the takeaway for now, and I believe everything we covered today should be as part of that. All right, so we'll go ahead and get started, and we're going to pick up where we left off last time with a problem about the relationship between temperature and vapor pressure. So this is probably the only, don't quote me on this, but I think it's the only equation for Chapter 9 that you have to worry about, and the only numerical type of problem you have to do. Almost everything in Chapter 9 is conceptual in nature. So what we have here is we have a liquid called diethyl ether. It's one of those things that you see in movies that people put each other to sleep with, where they put it on a rag, and it doesn't really work like that, but it looks good for the movies. And so anyway, this is a liquid that has an enthalpy of vaporization of 29.1 kilojoules per mole, and its vapor pressure is 0.703 atmospheres at 25 degrees Celsius. What would its vapor pressure be at 95 degrees Celsius? Now, before we even start a problem like this, we should think a little bit about where we're going and what our answer should look like. So we talked about how when you raise the temperature of a substance, the vapor pressure increases. You have more kinetic energy in the molecules, more molecules are able to escape into the gas phase, and so vapor pressure always goes up with temperature. So we're comparing 25 degrees Celsius, which has a vapor pressure of about 0.7 atmospheres, to 95. So the answer we get should definitely be bigger than 0.7. If it's not, then we automatically know that we made a math mistake. Now with this equation here, there's 2 forms of the equation, and I forgot to look up which one your book uses, but you might see it in both ways. The one that I introduced last time was this here, where P1 and P2 are the 2 vapor pressures we're considering. Enthalpy of vaporization divided by R, and then it's going to be in this way written as 1 over T2 minus 1 over T1. So we sort of flip the temperature terms. The other way that you might see it written sometimes, which is mathematically totally the same, it's just you put a minus sign out front and switch the temperature terms. Same thing on the left, but I'm going to put a negative sign there, delta H of vaporization over R, and this time it's going to be 1 over T1 minus 1 over T2. I meant to look up in your book which form they give you, because I haven't looked at that part of the book in a while. I don't know which one it is. Whichever form you remember is totally fine. They're exactly the same mathematically. You just have to remember to either keep the minus sign out front and keep the temperatures as T1 minus T2, or take the minus sign out and invert the 2 temperature terms. So I'm going to use this one here just because that's what I introduced, and it has less minus signs, so there's less chance of a math mistake, I think, later on. So in this problem here, what we're looking at is we do need the temperatures to be in Kelvin. So we're comparing 2 temperatures, T2 and T1. So T1 we're going to call the lower temperature, 298 Kelvin. T2 is 95 degrees Celsius, which we have to add 273 to get also into Kelvin, 368. So those are the 2 temperatures we're dealing with. And what we're given is that P1. P1 is going to be the vapor pressure at 298 K. That's the number that we're given, is 0.703. And so we're just going to be solving then for P2, the vapor pressure at the higher temperature of 368. So you have to keep the 2 terms have to be sort of correlated with each other. T1 and P1 have to correspond T2 and P2. If you keep all that straight, then it just becomes an algebra problem. This is the first equation we've had in this course, and you will see others in Chem 2, so there's going to be more of this in the future if you take that course. This is the first equation that uses natural log, so make sure you know the syntax for that in your calculator, especially the scientific calculator that you're going to be required to use for exams, because we haven't seen anything like that in this course. So what you're going to do is start putting in numbers. So natural log of P1. So for the pressure units, it doesn't matter what they are as long as they're the same. So in this case, If we put atmospheres in, that's fine, and then that means we're going to get a P2 that's also in atmosphere. So pressure units are fine as long as you recognize that they're the same for the ratio. What we have to be careful about with units is going to be the other terms. So as I said, the temperatures have to be in Kelvin, and then because R is 8.314 joules per kmol, so that's one of the values of R directly off the periodic table, and anytime we're dealing with energy, which we are here for enthalpy of vaporization, we want to use that value of R, but that's in joules, which means that our delta H has to be in joules. Most often delta H is going to be quoted in kilojoules per mole, but we need it to be in joules per mole for the units to work out. So we're going to make that 29,100 for delta H, joules per mole. So you have to multiply that by 1,000 to get it from kilojoules into joules. So that's something they have to remember also when you're, units are always important, of course. In this problem here, you have to make sure that we're using the right units for delta H, and then the joules will cancel out. And then for the temperature terms, we're going to have, this time in this form of the equation, T2, 1 over T2 minus 1 over T1. So the 368 Kelvin is going to go there, and the 298 is going to go there. So what we'll do then is this whole right side of the equation is just a bunch of numbers, so we'll just multiply and divide it out and get minus 2.234. And that should be unitless because you have joules canceling out, moles canceling out, Kelvin canceling out. So it's a unitless quantity. And so then what we have is the natural log of 0.703 over P2 equals minus 2.234. And then what we also have to remember from our previous math courses is that if you want to get rid of a natural log, you have to do the e to that power, the natural, the Euler's number. So you're going to have, to get rid of that, you take 0.703 over P2 is going to be equal to e to this power, minus 2.234. So again, make sure you know the calculator syntax for doing that. And then we just have to cross multiply and divide. So e to the minus 2.2034 is 0.107. And so then what we finally solve for is that P2 is equal to 6.56 atmospheres. All right, so I'm not going to spend a ton of time in the algebra, so make sure you follow that. And if you have any questions later on, let me know. And try it yourself, definitely, to make sure you follow that if it was unclear. But it is a bigger number than 0.7, so the temperature was raised, and the vapor pressure should also be higher, as we already talked about. All right, so again, that's probably the only equation we'll deal with. So any other questions on that? All right, so what we're going to get into for most of today is phase changes, but before we talk about that, there's just one last sort of summary slide about how intermolecular forces and vapor pressure relate to each other. So we introduced vapor pressure already, and we've now talked about how it depends on temperature. Let's also, in a qualitative sense, talk about how it depends on the intermolecular forces. Again, those are the forces of attraction between molecules in any condensed phase or any real gas. So the relationship between intermolecular forces and vapor pressures is as follows. If you have, and I think this is a fairly logical statement, just do a little bit of a thought experiment here. So if you have stronger intermolecular forces, if the molecules are held together more tightly, more strongly, then you're going to have fewer of them escaping into the gas phase, so your vapor pressure would be lower. So if you have stronger IMFs, you're going to see lower vapor pressure. So we learned last time how to sort of qualitatively predict, in a relative sense anyway, the strength of intermolecular forces. And so if the intermolecular forces are predicted to be stronger, the vapor pressure is predicted to be lower. And that's again because vapor pressure requires molecules to escape into the gas phase, and if they're held together more strongly, that won't happen as much. So it requires molecules to escape the surface. If they're held strongly to the surface by strong IMFs, then that's not going to happen. And then the other one, which is also fairly logical and follows really the same sort of argument, is that the relationship between intermolecular forces and the enthalpy of vaporization. So remember, enthalpy of vaporization is how much energy do we have to put into a substance to vaporize 1 mole of it, to get 1 mole of the liquid molecules to escape into the gas phase. And so if you have stronger intermolecular forces, it's going to require more energy to vaporize the molecules, and that means you're going to have a larger enthalpy of vaporization. Enthalpy of vaporization is always endothermic. You have to put energy into something to vaporize it. And it really follows the same argument. If you have stronger IMFs, more energy is required to break those. And you have to break apart all the IMFs to get into the gas phase. All right, so that's kind of just a quick summary of those relationships, which I think follow pretty clearly from stuff we've already talked about. But now we kind of have, relationships that involve vapor pressure and temperature, vapor pressure and intermolecular forces being the two big ones that you'll want to be able to sort of qualitatively rank. All right, but what we're going to move into now for the rest of today is a lot of talk about phase changes. And so first we want to give some more precise definitions of them. So we've already talked about boiling point and melting point, and we said that boiling point is the temperature at which molecules escape to the gas phase, and melting point is the temperature at which a solid is converted to a liquid. We kind of gave those very general definitions. There's a little bit more to it than that, just from from the standpoint of being precise and accurate with this. So boiling point is going to be defined as the temperature at which the vapor pressure equals the atmospheric pressure. Because then when that happens, that's when molecules in net are going to start escaping into the gas phase. So the vapor pressure increases with temperature, and once the vapor pressure equals the surrounding atmospheric pressure, that's when we say we've reached the boiling point. And so what that means, and we'll talk about this in more quantitative terms in a little bit, the boiling point is dependent on what the atmospheric pressure is around that substance, because it's whatever temperature is required to get the vapor pressure equal to the surrounding atmospheric pressure, whatever that number is. Usually close to 1 atmosphere, but not necessarily, depending on where you are. And then boiling has an associated enthalpy, which we've already talked about, which is the enthalpy of vaporization. So that's just a review of what we've already talked about. Enthalpy of vaporization, the enthalpy change associated with vaporizing 1 mole of a substance. And then the melting point has a really strange, precise definition. Again, if you just want to think about it as, it's the temperature at which the solid converts to a liquid, that's accurate and that's a really good physical representation of what you're talking about. But its precise definition is that it's the temperature at which the vapor pressures of the solid and liquid phases are equal. And again, this definition is not intuitive or really something that you can easily visualize. So we want to be familiar with it, but it's not really the way we usually think about it. But it's the temperature at which the vapor pressures of the solid and liquid phases are equal. So solids have vapor pressure as well, typically much lower than the corresponding liquid vapor pressure. But there is a vapor pressure associated with solids also, and the temperature at which those two phases have the same vapor pressure is called the melting point. So that's the precise definition of melting point. And the associated enthalpy of this is called the enthalpy of fusion. We already introduced that a little bit, and we're going to use it again today in a more numerical context. And again, we call that process melting when you're going from, and this is the enthalpy change associated with the solid to liquid transformation. So that's going from solid to liquid. We call that enthalpy of fusion, also a positive number. And then finally, what we also have for every substance is what's called its normal melting or normal boiling points. And those are the corresponding boiling point and melting point temperatures when the surrounding pressure is exactly 1 atmosphere. And so what that means, we already said that boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. So for the normal boiling point, that means the vapor pressure has to equal exactly 1 atmosphere. So the vapor pressure equals 1 atmosphere at the normal boiling point. So when we say that the boiling point of water is 100 degrees Celsius, what we really mean is that the normal boiling point of water is 100 degrees Celsius. That means that's the boiling point at 1 atmosphere of atmospheric pressure, and it means that the vapor pressure at that temperature is exactly 1 atmosphere also. So that's what we usually, the boiling points that we quote for specific substances always are the normal boiling points, the boiling points that they would have at 1 atmosphere. But if the atmospheric pressure is different, then the boiling point is going to be different. And so we're going to see that here in an example problem, which is sort of another complementary or alternative way of using that same relationship that we just talked about. So we have a relationship between temperature and vapor pressure that also involves enthalpy of vaporization. So if we have a liquid that has an enthalpy of vaporization of 35.5 kilojoules per mole and a normal boiling point of 122 degrees Celsius, what is this boiling point at the top of Pikes Peak? That's one of the tallest peaks in Colorado, or maybe the tallest one, I forget. And there the barometric pressure is only 457 millimeters of mercury. Okay, so in this case here, it may not look the same, but we're actually using the same relationship between vapor pressure and temperature that we already used, which is that the natural log of the ratio of the vapor pressures is equal to enthalpy of vaporization divided by R, and then the two temperatures, T2 minus T1. All right, so what we're looking for here, let's sort through the given information first. Enthalpy of vaporization is given to us. There's no way for us to find that from scratch. Normal boiling point of 122 degrees Celsius. So what that statement tells us is that at a temperature T1 of 122 degrees Celsius, the vapor pressure at that temperature, which we'll call P1, is exactly equal to 1 atmosphere, or 760 torr, since we're using torr in this problem. So when you say the normal boiling point is 122 degrees Celsius, that statement tells you that at that temperature, the vapor pressure is 1 atmosphere. So that gives us one of our pressure-temperature pairs. What we're looking for is the boiling point where the barometric pressure is 457 millimeters. So what we're trying to find is what is the temperature when the vapor pressure is equal to that. So we're going to call that our P2. That's the second vapor pressure. So again, when vapor pressure equals atmospheric pressure, that's when you get to the boiling point. And so we're looking for the temperature that corresponds to that. Okay? So we have a lower atmospheric pressure at the top of a mountain, so we'd expect the boiling point to go down. Let's see if that's true mathematically. So we can start plugging in the numbers now. So we have the two pressures. P1 we said is 1 atmosphere, or we'll just put it in torr, 760, since the other pressure is in torr. P2 is 457 torr, or millimeters of mercury, I guess is how it's stated, but those are the same. And then we have enthalpy of vaporization converted to joules again, 35,500. So it's 35.5 kilojoules converted into joules for this problem, so that we can cancel out with the 8.314, which is in joules per k mole. And then we have the two temperature terms. So T2 is the temperature we're solving for. That's where we're trying to find at what temperature does the vapor pressure equal 457 torr. So that's our unknown. And then T1 is 122 degrees Celsius, which is 395 Kelvin. All right, so our only unknown is T2. I guess I can walk you through the algebra a little bit on this. So if we take the natural log of this ratio, we get 0.5086. And then when we divide these two and distribute the terms, we get 4269.9 over T2 minus 10.81. So I'm working through some of the intermediate steps because this algebra is a little bit different than stuff we've done before. But we're just distributing the terms over here, dividing these two numbers and distributing to get this. And then we just do a little bit more algebra to solve for T2, which should be 377 Kelvin, or 104 degrees Celsius. I didn't specify units here, but Celsius is more commonly used, I suppose, in quoting temperatures. All right, so it is lower. When you go to the top of the mountain where the atmospheric pressure is lower, the boiling point also drops. So this reminds me of something that I used to always be fascinated about when I was a kid. I don't know if they still do this because I don't eat this kind of food anymore, but if you have like a box of like macaroni and cheese or pasta, and it says on the back, you know, at high elevation, cook for, you know, a longer time. So, you know, if it might say like at sea level, cook for 5 minutes, but at high elevation cook for 8 minutes. And I always wonder, like, why is that? Well, that's because the boiling point of water at high elevation is lower. So if it's a lower boiling point, the water temperature won't be as high, and it'll take longer to cook the food. So this is a demonstration of that, not with water, but with some other substance that boils at a similar temperature. And you can see that at the top of the mountain, where the pressure is a lot lower, the boiling point does get significantly lower as well. All right, so any questions on that? All right, now I guess I misspoke a little bit when I said that this is the only type of numerical problem we're going to do. We have another situation here, which are called heating curves, or calculating the heat associated with phase changes and temperature changes and things like that. Now, this doesn't really involve any new equations, though. This just involves us to put together a few things you've already learned. And what we're going to basically talk about is if we take a substance and we just heat that substance up over a certain temperature range, where we're going to raise the temperature of the substance, and then we may or may not go through phase changes depending on what temperature we get to, how much total heat is required for that. So let's talk about then, before we get into the numbers, let's talk about what happens if we take a sample of ice, which is solid water, and we heat it at a constant rate. And so what we're going to be plotting here on the y-axis is the temperature that we get to in degrees Celsius. And we're just going to sort of plot what happens as we add heat to this at a constant rate. So what we're going to do is if we start with ice at minus 20 degrees Celsius, the freezing point of water is 0, so at that temperature it's going to still be solid ice. It's going to be in the solid phase at that temperature when we're below the freezing point or melting point. And so what happens is when you heat this up initially, you're going to raise the temperature, but it's still going to be ice. So here we just have ice. But then once you get to 0 degrees Celsius, 0 degrees Celsius is the temperature at which the ice will melt into liquid. You're going to continue putting heat into the substance, and all of the ice is going to convert into liquid water. So there's going to be a phase change that occurs as the solid melts and it goes to liquid. So for some period of time, you're going to have the phase change is going to happen at a constant temperature. So until all of the ice melts into water, you're not going to be changing the temperature any further. All the heat that's going in is going to just be melting the substance, changing the solid into liquid. So at this temperature of 0 degrees Celsius, until all the ice is melted, you'll have a mixture of both ice and water. Once all of the ice is melted into liquid water, then you're going to start raising the temperature again as you continue to add heat. And so we know that the boiling point of water is 100 degrees Celsius. So until we get to 100 degrees Celsius, it's going to be just liquid water, and you're going to raise the temperature as you add heat to it, just like the stuff we talked about in Chapter 7. You add heat to something, MC delta T, you're going to raise the temperature of it. So in this range, we have water here until we heat it up to 100 degrees Celsius. And then once you get to 100 degrees Celsius, as you continue to add heat, you're going to then boil the water, because the normal boiling point for water is 100. So once you get to 100, if you keep pumping heat into it, think about putting a pot of water on the stove. You're going to raise the temperature of the water. Once it gets to 100 degrees Celsius, then it's going to start boiling. And so in that period of time, it's going to stay at a constant temperature of 100 degrees Celsius until all of the water is boiled. So in this range, you have water and water vapor, or what's sort of commonly referred to as steam. And then once you get to 100 degrees Celsius, and you've boiled all the water, and now you have gas phase water, or what we colloquially refer to as steam. If you keep heating it up, you're going to keep raising the temperature of that. And so this is going to be here just steam in this phase. You're going to keep raising the temperature as you continue to add more heat. So the point is, whenever you heat a substance up, there's really only two things that can happen. If you're in a single phase of matter, you're going to just raise the temperature, and we're going to use, as we'll see, MC delta T to relate the amount of heat to that temperature change. And then if you get to a phase change temperature, 0 degrees or 100 degrees for water, then you're going to undergo the phase change, and the amount of heat associated with that depends on the enthalpy change for that, either the enthalpy of fusion if you're melting it, or the enthalpy of vaporization if you're boiling it. And so really it's just putting those two concepts together. What we learned in Chapter 7, Q equals MC delta T, and now in combination with phase change enthalpies here. So most of the problems that you'll do in this regard are not going to be this many steps, but this is basically the most complicated it could be. And I'll do an example that has all of these steps just so you can put it all together. In reality, most of the ones you'll see on homework assignments and tests are going to be like 2 or 3 steps. Warming it up over temperature range, maybe one phase change or so, but this is sort of encapsulates all the different possibilities we would have. Now, one thing that I wasn't particularly careful about here is that for these portions of the diagram where we're raising the temperature, the slopes should not all be the same. They kind of actually are, I think, in the way I drew, are not very different from each other. The slope of that's going to depend, how fast the temperature increases is going to depend on the heat capacity, C, the specific heat capacity of that substance. So if it has a low heat capacity, you don't need to put a lot of heat in and you'll get a big temperature change. If it has a higher heat capacity, you're going to have a steeper slope, more heat's required to raise the temperature, or maybe it's the opposite, I might have misspoke. But nonetheless, that heat that you put in to raise the temperature is going to be MC delta T, so it is going to depend on that heat capacity C. And it's important to recognize that all three phases, the solid, the liquid, and the gas, which is called ice, water, or steam, if you're talking about the substance water, all of those are going to have different specific heat capacities. So when you're calculating, when you're using Q equals MC delta T for this phase, or this phase here, you have to make sure you use the correct specific heat capacity for the phase that is present at that temperature. So make sure we keep that straight. Now we have different specific heat capacities depending on which phase we're in. So that's another little added wrinkle to this. But really the math is not difficult, it's just making sure that we use the right steps and put them all together. Okay, so let's do an example problem that really has this exact same process here. We're starting with ice, 5 grams of ice at minus 20 degrees Celsius, and we're going to heat that until it reaches the gas phase with a temperature of 140 degrees Celsius. So again, in order for that to happen, if we're starting at solid ice, we have to raise the temperature to 0 degrees Celsius, melt the ice, raise the temperature to 100 degrees Celsius, boil the water, continue raising the temperature until we get to our stopping point of 140. So there's going to be like 5 different steps involved. Again, this is the most complicated it could be. We won't see them usually this complex on homework assignments. Okay, so what we're going to do is we're going to calculate the heat associated with each of those 5 distinct steps, and at the end we're going to add them all together. So let's call phase 1, or step 1 if you want to call it that. I'm going to use step because phase kind of is confusing. We're talking about phase changes. So step 1, we're starting at minus 20 degrees Celsius, and we have to warm it up to the freezing point before anything else will happen. So we're going to warm the ice from minus 20 degrees Celsius to whatever temperature the phase change occurs, which for water is 0 degrees Celsius. If it was a different substance, then it would melt at a different temperature, so you have to make sure you're familiar with what that is. That would be given in the problem if it wasn't water, because water is the only one where we expect you to know the freezing point and boiling point. But for water, it's 0, so that's what we're going to warm it up to. And whenever you're in a single phase, in this case solid, and you're just raising the temperature by heating it up, that's just going to be MC delta T. So the heat associated with that step is going to be MC delta T. Now, the only thing we have to be a little bit careful about here, though, and this is something that we haven't seen yet until we start talking about phase changes, is that, as I already sort of alluded to, there's 3 different specific heat capacities for the 3 different phases of matter that we have for any substance. So here we're talking about solid water, which is ice, so we want to make sure that we use the heat capacity for the solid, not the other ones. So 4.184, the number that we use all the time in Chapter 7, that only applies to liquid water. If we're in the solid phase, ice, or the gas phase, vapor, you have to make sure you use the proper one. So it's going to be 2.09 for this one. So we have 5 grams of the substance. The correct specific heat capacity to use is 2.09. And then the temperature change, we're going, let's do degrees Celsius, since that's the temperature we're using. The temperature change is minus 20 to 0, so that's a temperature increase of 20 degrees Celsius. Delta T is 20, 0 minus 20. And so what we get for this is 209 joules. I did not specify which units we're going to use for the final answer, but I should have specified that it'll be kilojoules. So it's going to be 0.209 kilojoules. That's the only other thing you have to be a little bit careful about with problems like this, is usually the Q equals MC delta T steps are going to be given to you in joules, because specific heat capacities are usually quoted in joules per gram degree Celsius. As we'll see, the phase changes are usually quoted in kilojoules per mole, and so you have to be aware of units when you're doing this, as always. All right, so we've gotten the ice up to 0 degrees Celsius, so then the second step is going to be to melt the ice. And again, similar to some things we talked about in chapter 7, if we want to figure out how much heat it takes to melt the ice, we need to use the enthalpy of vaporization, or sorry, the enthalpy of fusion, which is this number here, 6.02 kilojoules per mole. Now this is the heat required to melt 1 mole of ice. We don't have 1 mole of ice, so we have to multiply this number by the number of moles of that substance that we have. So the heat for this step is going to be the moles of ice that we have multiplied by the enthalpy of fusion. Enthalpy of fusion is how much heat per mole. We multiply by how many moles we have. In this case, we're not directly given moles, but it's water, so we know how to convert. So the moles that we're going to have for any of these steps, whether it's solid, liquid, or gas, you still calculate moles the same. It's the same substance. So we have 5 grams of water, and then we just use the molar mass of water. 1 mole has a mass of 18.02 grams. So we get 0.278 moles. So for any of the steps that involve phase changes, we're going to need to use moles of substances because the phase change enthalpies are per mole, and so that's the number we'll use for any step that requires that. Just one other thing to always be aware of in problems like this, it's not impossible that the enthalpy of vaporization can be given per gram instead. So standard, conventional way to report it is per mole, but they could also be reported per gram on a mass basis. So just look carefully at the units that you're given to make sure you use the right quantities. But this time it's per mole, so we're going to use moles of water, which is 0.278. And then the phase change enthalpy for melting, which is called delta H of fusion, is 6.02 kilojoules per mole. And so that comes out to 1.67 kilojoules. All right, so that's step 2. We're 40% there. Again, we're not going to usually have, or I don't think we'll ever have homework problems that are this many steps, but this gives you the full picture. All right, third step. Now that we've melted the ice, we're in the liquid phase. We're going to heat it up until we get to the next phase change. So we're going all the way to 140. The next phase change occurs at 100 degrees Celsius, so we are going to go to that phase change temperature first. And so what we're going to do there is we're going to warm the water from 0 degrees Celsius, where it's first going to be formed as during the melting process, up to where the next phase change occurs, which is 100 degrees Celsius. And so again, we're in a stage where we're just warming the substance up, changing the temperature, so it's going to be MC delta T. But this time we're going to use the liquid heat capacity because we're in the liquid phase now after melting. And it's going to be the same numbers other than a different value of C. So 5 grams still of the substance. This time we're going to use the more familiar 4.18 or 4.184 if you want to be more precise, joules per gram degree Celsius for heat capacity. Delta T in this case, 0 to 100 is 100 degrees Celsius. We're raising the temperature by 100. And so that comes out to 2,090 joules or 2.09 kilojoules. We'll do everything in kilojoules so that we can add them all up at the end. All right, so that's step 3. Oh, I did not give myself enough space. Dang it. I thought I had an extra page in here. Let me try to insert one. How do I do that? Did I put it in the right place, or did I put it? Oh, I put it before. Shoot. One of these days I'll learn how to use this program. Right. Edit, page, append. I guess that's after. Okay, so that gives us more room to work. Sorry about that. I should have made the notes a little bit better. All right, so we have. That's step 3, we got warming, and then now that we're at the next phase change temperature, we're going to go through that phase change. So we're at 100 degrees Celsius, and now we're going to blow the water. So the heat associated with this is going to be the moles of water times the enthalpy of vaporization this time, so since we're doing boiling. So we calculated before that there's 0.278 moles. And then we have to make sure we use the correct phase change enthalpy, which is vaporization this time, 40.7. So 40.7 kilojoules per mole multiplied by 0.278 is 11.3 kilojoules. That's the amount of heat associated with boiling. And then finally, the last step, we're going to go all the way to 140 degrees Celsius. That's where we're told to stop. So we're in the gas phase, or what we call steam for water, and we're going to warm that up to the final temperature. So the steam is first formed at 100 degrees Celsius when we boil, and then we're going to warm it up to 140, which is where we're told to stop in this problem. Okay, so that's the last step, warming the steam. So now it's just a warming process, so it's going to be MC delta T. This time we have to use the heat capacity of the gas phase, the steam, because we're in the gas phase now. So it's the same mass, 5.00 grams. We have to make sure we go to the right heat capacity. Heat capacity for the gas phase of water is 2.00, similar to the solid phase, coincidentally. There's no real rhyme or reason to that. 2.00 joules per gram degrees Celsius. And then the temperature change this time is 100 to 140, so a difference of 40 degrees Celsius. So that comes out to 400 joules, or 0.4 kilojoules. All right, so now we have all of the numbers. We have to add them up to get the total amount of heat that this process required. So the total heat is just all these numbers added together. 0.209 kilojoules, which was how much it required to warm up the ice. 1.67 kilojoules, which is how much was required to melt the ice. 2.09 kilojoules, which was how much was required to warm up the water. 11.3, which is how much was required to boil the water. And then finally, the last number we just got, 0.4 kilojoules to warm up the steam. So all those numbers added together with the correct number of decimal places at the end is 15.7 kilojoules. So as we can see, most of that energy that was required, 11.3 out of the 15.7, was just to boil the water. And that's pretty common because boiling something requires you to break all the intermolecular forces to have all those liquid molecules escape into the gas phase. So that requires a decent amount of energy compared to just warming it up or doing the other phase changes, which don't require you to break all the intermolecular forces like they do for boiling. All right, so that's, again, as complicated as it gets, but really there's only two possible mathematical relationships you have to use, either MC delta T if you're warming it up, or the phase change enthalpy multiplied by the amount of substance if you're doing that phase change. So you just have to keep track of which temperature ranges each of the phases exist in, which temperatures the phase changes occur at, and make sure you account for all the different things that will happen as you warm up that substance. All right, so any questions on that one? All right, I guess I'll torch you guys with one more example. This one is not as extensive. There's less steps in this one. All right, so we have another one that's similar. Now, the only thing that we have to do a little bit differently here is that here what we're doing is we're cooling the substance down. So we're starting with 0.333 moles of gaseous ethanol. So ethanol is normally a liquid at room temperature, but at 300 degrees Celsius, it's going to be a gas. And then we're going to cool that down all the way to 25 degrees Celsius, which is where it'll be a liquid at that temperature. So we're going in the opposite direction this time. Instead of warming it up, we're cooling it down. So that's just going to change the sign of everything. So it's going to give you the same mathematical relationships, but now instead of putting heat into the substance, we're going to be releasing heat as it cools down. So everything's going to be a negative term in this case. So we want to calculate the heat when this all happens. So we have basically the first step here is we're in the gas phase and we're going to cool it down until it gets to the boiling point. So whenever you're in the gas phase, if you're cooling it down, you're going to cool it until you get to the boiling point, and that's when it's going to start condensing back to the liquid. So the boiling point for this substance is 78.5 degrees Celsius. So our first step is going to be to cool down the vapor from where we're starting, which is 300 degrees Celsius. I would not recommend playing with ethanol vapor at 300 degrees Celsius because there's a good chance you'll have a fire. But if you don't have oxygen around, you'll be okay. But if you cool that down from 300 degrees Celsius to 78.5, at that temperature, that's when it's going to start condensing back to the liquid. So first you have to cool it down to that temperature before anything else will happen. And so when we're cooling a substance, it's still going to be MC delta T. The only difference here, first of all, we have to make sure we use the right heat capacity, which is for the gas phase. And then our delta T is going to be negative because we're cooling it down. Okay? So we have 0.333 moles of ethanol. This time I gave it to you in moles, but the heat capacities are still in grams. And so the mass of ethanol, sorry. This is a terrible problem. Well, it's not terrible, but anyway, I should have told you that the formula for ethanol is C2H5OH, so that you can calculate the molar mass and get the grams. So the grams of ethanol, you're not expected to know the formula of that, so don't worry if you didn't. Most likely you didn't. 0.333 moles. And then I thought I had the molar mass of this somewhere, but I don't. So that's going to be, let's just do it roughly, 12 plus 6 is 18. Sorry, 24 plus 6 is 30 plus 16, 46. About 46 grams per mole. I apologize for that. I should have included that information. So the molar mass of the substance is 46, and we need that because we need the grams of substance to be able to do the heat terms here, because their heat capacities are in grams as they usually are. All right, so I left out some key information here, which I thought I had, but I guess not. And anyway, that comes out to roughly 15.3 grams. All right, so that's the mass that we have. This time we had to take the number of moles that we were given and convert it into mass for this step, opposite of what we did before. But now that we have that, we're going to use this heat capacity here because we're in the gas phase, 1.43. And then our delta T, again, we have to make sure we're keeping straight which direction we're going. We're going final temperature of 78.5, that's where we're stopping, and we're starting at 300. So it's going to be a negative delta T when we're cooling down. So we get minus 4,859 joules, which is minus 4.86 kilojoules, okay? So all the terms here should be negative when we're going from higher temperature to lower temperature, whether it involves phase changes or not. All right, for step 2, once we've gotten to the boiling point, which is also the point at which, then that's the point where the vapor is going to condense back into a liquid. So at this temperature of 78.5 degrees Celsius, we're going to now condense the vapor at a constant temperature until all of it is condensed back into the liquid phase. And the heat in this case is going to be the moles of substance multiplied by the phase change enthalpy. Now we have to remember that what we talked about last time is that the enthalpy of vaporization is always a positive number. In this case is 40.5 kilojoules per mole. The enthalpy for condensing the substance is just going to be equal to that but opposite in sign, so we're going in the opposite direction. We're going from gas back to liquid. So it's going to be the negative of the delta H of vaporization when we're condensing a substance. We're going in the opposite direction. So we have 0.333 moles, and the enthalpy of vaporization is 40.5, so it's going to be minus 40.5 for condensation. And that gives us minus 13.5 kilojoules. Okay, so that's our first number. That's our second number there for condensing. And then finally, the last step is we're cooling this all the way down to 25 degrees Celsius. So it's going to stay in the liquid phase. I didn't give you the freezing point for ethanol, but the freezing point for ethanol is like minus 60 or minus 70, so it's really low, a lot lower than water. So you're not told what the freezing point is, and we're telling you that you're stopping at liquid ethanol. So we can assume that we're not going to go through another phase change. We're just going to cool it down to that final temperature. So our last step is going to be to cool the liquid that we formed via condensation from the boiling point where it first forms, 78.5 degrees Celsius, to the stopping point of 25 degrees Celsius. And again, it's just a temperature change, so it's going to be Q is equal to MC delta T. We calculated before that the mass is 15.3 grams. We're in the liquid phase now, so we have to use the other heat capacity that's given to us, which is 2.45. And then delta T, final minus initial. Final temperature of 25 degrees Celsius, initial temperature of 78.5. So again, it's a negative delta T because we're cooling down. And so that gives us minus 2005 joules, or if we round it appropriately to kilojoules, minus 2.01. All right, so those are the three numbers we need to add together now to get the total heat. So minus 4.86 kilojoules when we cool down the steam, or the vapor. In this case, it's not water, so it's just called vapor. Minus 4.8 kilojoules. The second term was minus 13.5. That's the amount of heat that was involved with condensing it. And then the third one, minus 2.01. And so what we end up with is minus 20.4 kilojoules. Negative term in this case because we're cooling the substance down, going from gas to liquid, which is an exothermic process. Okay? So same concept, just be aware that the signs can change depending on whether you're going from lower temperature to higher temperature or higher temperature to lower temperature. That's the only difference between this one. So it's just those two steps, phase change or Q equals MC delta T, heating it up and cooling it down, combining the appropriate steps and make sure the signs are correct. So any questions on that concept or that type of problem? All right, like I said, they won't typically be, this is probably as complicated as it'd be, just 2 or 3 steps in your assignments, but make sure you're familiar with the different ways that they can be set up. All right, the last thing we're going to cover related to liquids is called supercooling and superheating. This is just a quick sort of definition and concept to be aware of. So supercooling is actually kind of interesting. So supercooling is when a liquid is cooled below its freezing point but doesn't freeze. So supercooled water would be liquid water that exists, at least for a period of time, below 0 degrees Celsius. You've gotten below the freezing point of that substance, but it hasn't frozen yet. This actually, supercooling has a pretty interesting biological context. So I think I may have mentioned before, I have an identical twin brother, and he does research on insects that can survive really cold temperatures. And so those insects are able to, they have proteins and things in their body that allow the liquid inside of their body to supercool so that it doesn't freeze. Because you can imagine if the inside of something's body freezes to a solid, that's bad news for them, right? So they're able to do this in certain extreme environments to prevent their whole bodies from freezing, and that's the process called supercooling. Now, we don't need to know a lot about supercooling for this course, but really the main reason that it even occurs at all, at least without any sort of external stimulus. I mean, as I said, a lot of organisms use proteins or sort of like ionic gradients and things to control this process. If it just happens naturally in pure water, it occurs because it takes some amount of time for those liquid molecules to sort of organize and become a solid. So the branch of chemistry that deals with how long processes take is called kinetics. So when you get to the freezing point, it should get to a solid at some point, but it doesn't necessarily happen instantaneously. There's some period of time that it might take for that to happen. So for that period of time, before the water molecules can, or whatever liquid molecules can organize and freeze into a solid, it can exist as a supercooled liquid, where it's below the freezing point, but still in the liquid phase. Superheating is sort of the opposite situation, is when a liquid is heated above its boiling point. So in case of water, it'd be above 100 degrees Celsius, but it doesn't immediately boil at that temperature. And of course, the reasons for this are different because, we don't have, in the case of going from liquid to gas phase, we don't need the molecules to organize. They're just going to fly everywhere, into space. So it's not the same reason for it. Why does it occur? There's a couple of reasons why, but one would be uneven heating. So there could be a region of the liquid where the temperature is above the boiling point, but it's surrounded by cooler liquid, so that doesn't have enough energy to escape through that cooler liquid. Or, as we know, every liquid has surface tension, and so sometimes you just have to get the boiling process to be happening fast enough for those to start breaking through that surface tension. If there's just a little bit, if it's just starting to get to the boiling point, if it's just at 100 degrees Celsius for water, you still might not have enough energy to break that surface tension, even though in reality it should. So we don't really know much about these. We just want to know the definitions of them and a little bit about why they occur. So that's just a small aside to finish up our discussion of liquids, and this of course is related to phase changes as well. All right, but the thing we're going to cover for the rest of today, and I believe, as I said, is the last topic that's going to be relevant to the third midterm exam, are what are called phase diagrams. So we've talked about now, at some level, all three phases of matter, which are mainly solid, liquid, and gas. And a phase diagram is one that sort of summarizes the different conditions of temperature and pressure at which all those different phases would exist for a substance. So it's a temperature pressure diagram. One axis is going to be temperature, one axis is going to be pressure. So if I want to know what phase would water be in at 105 degrees Celsius and 6 atmospheres of pressure, then I can go to the phase diagram, find that temperature and pressure, and the diagram will tell me whether it's solid, liquid, or gas at that temperature. So it's a temperature pressure diagram for a substance, and it shows the conditions under which it exists in different phases. So at any given temperature and pressure, you can consult the diagram and figure out which phases exist at, or is it a mixture of phases, if it's right at the phase change, conditions, and so on. So it's a two-dimensional plot with an x and y axis. So the y-axis in this case is going to be pressure, and the x-axis is going to be temperature. And so what that's going to then do is you're going to have basically lines on this diagram that divide up the different phases, which at minimum are going to be solid, liquid, and gas. So you're always going to have at least 3 regions on a phase diagram: solid, liquid, and gas. Now what you'll sometimes see for certain types of substances, we'll give an example, at least one example of this today. Sometimes you'll have multiple solid phases present. So the example we'll give today is carbon, which has 2 major solid phases, graphite and diamond. So certain substances have different forms that they can exist as in the solid phase, and the phase diagram will show those kind of as separate regions of the diagram, because usually those 2 forms would exist under different conditions. So there are a lot of substances where that's true, where the solid part of the diagram is more complicated because there's more than one solid phase that can exist. As we'll learn in the second half of the chapter, what that typically refers to is that there's different structures for that solid. So the atoms or the molecules can arrange themselves in different patterns depending on what conditions they're under, and that gives rise to 2 distinct solid phases. Same chemical compound, but different properties as a result of the different structures that they have. So the phase diagram will show that, though. Now, why are phase diagrams useful? Well, there's a lot of things that you can do with them. We're going to have a whole bunch of example problems at the end that kind of shows all of this, is that you can predict phase changes, so what conditions will the phase change. You can use it to predict vapor pressures. We have equations for vapor pressure, of course, but if you want to just quickly predict it from a diagram and just kind of ballpark what it would be, you can use the phase diagram to do that, because the vapor pressure is going to be the pressure at which the liquid and the gas phases both exist at the same time. So there's a line that divides those 2 that gives you the vapor pressure at a different temperature. And there's other properties that you can also predict that we'll see. And you're able to do this under a wide range of conditions. And, because for a lot of phase diagrams, I mean, it depends on the substance and everything, but they'll have temperatures that go out to 1,000 Kelvin or more, and they'll have pressures that go up to hundreds or thousands of atmospheres, depending on what substance it is and how extreme of conditions it's been studied under. So under that huge wide range of conditions, you can make predictions about how it'll be. And there's a lot of other applications of phase diagrams in chemistry that are a bit advanced for this course, but they are important. So what we're going to start with first is the phase diagram for water. And so what we're gonna see here is what we have is pressure on the y-axis, this time in millimeters of mercury. So it's pretty small scale in this kind, just one or two, about 2 atmospheres or so, and then temperature that goes from 0 or so to 100. All right, so let's talk about the different features of this diagram here. So the first thing we're going to do is talk about what these different lines mean. Okay, so this line here is going to be the solid-liquid line. So if you go to the left of this line, which is lower temperature, that's where you're going to exist as a solid. If you go to the right of this line, which is higher temperature, that's where it exists as a liquid. All right, so that's your solid-liquid line there, shown in red. And by following this line, we can predict what the melting point would be under any different set of conditions. So here at 760, which is 1 atmosphere, if you follow that down, it'd be exactly 0 degrees Celsius. So that allows us to predict the melting point at different pressures. Now the other line that we haven't labeled yet is the liquid gas line. And again, we kind of already know about how these phase changes work. So if you're on the left of this line, which is lower temperature, that's liquid. If you go to higher temperature to the right of this line, that's where it's going to exist as a gas. And of course, there's also a pressure dependence to that, but that's going to be the 3 regions. So in a typical phase diagram, let me do that in blue so it's the same color as the rest, there's nothing special about it. In a typical phase diagram, you're going to have those 3 regions: solid all the way to the left, liquid in the middle, gas all the way to the right. Okay, so that's the 3 regions, and that green line there then divides the liquid and the gas phases. So we call it the liquid gas line. And this allows us to predict the boiling point at different pressures. Again, we have an equation for doing that as well, but this diagram allows us to just do it in diagrammatic form. So at 1 atmosphere, that's 100 degrees Celsius. We follow that line towards exactly 760 torr, 1 atmosphere, that'd be 100. But then as we change the pressure, we're going to have, as we talked about, lower and lower boiling points as a result, and that would predict this. All right, so there's a couple of points then in this diagram that I want to label here. So again, if we follow over from 760 millimeters, which is 1 atmosphere of pressure, the point where that intersects the solid-liquid line, which I'll call point A here, is going to give us the normal melting point. And then when we continue over at 1 atmosphere of pressure to this point here, where it intersects the liquid gas line, which I'll call B, that gives us the normal boiling point. But we can do this for any other pressure as well that's shown in the diagram. So normal boiling point, normal melting point are at exactly 760 millimeters or 1 atmosphere. So we can, wherever those phase change lines intersect, is going to give us the temperature as we go down to the x-axis, so 0 and 100 as we said. But if you wanted to predict those temperatures at any other pressure, you could do it as well by just following the solid-liquid line for melting or the liquid gas line for boiling. All right, any questions on the basics then of a phase diagram? All right, so there's some additional insights that we can get from this. So I have a smaller version of that shown here. All right, so one thing we'll notice is that the slope of this line here is actually pretty telling. So this is our solid liquid line here. This line here that I'm following with a highlighter right now. I'm trying not to trace too much, but that's our solid liquid line. You notice that the slope, it's almost straight up and down, but it's a little bit negative sloping. It goes, top right, top left to bottom right a little bit. So it has a negative slope. And so let's think about what that means a little bit. So if we're here at this point in the diagram, it'd be easier with a more exaggerated slope, but if we're at this point in the diagram, which is solid right now, this is solid, liquid, and gas. If we're at this point in the diagram and we raise the pressure up, eventually we're going to cross the solid liquid line and be back into the liquid region. So basically in this substance, when we raise the pressure at a constant temperature, we can convert it from a solid to a liquid. Now what does that tell us? So when you have a negative slope for your solid liquid line, if we increase the pressure, that will convert from a solid to a liquid. And then what that tells us is that, think about what happens when we're raising the pressure. We're taking the substance and we're compressing it, we're compacting it into each other, and eventually it's going to go from solid to liquid. So we're increasing the density of the substance as we pack it together more and more, and then eventually it changes to a liquid. So that tells us that the liquid is more dense than the solid, or water. This is actually somewhat abnormal. It's more common for the solid to be more dense than the liquid, but in water it's the opposite. The liquid is more dense than the solid for water. And you guys know that because you know that ice cubes float on water. That's because the solid phase of water is a little bit less dense than the liquid phase. And the slope of this solid liquid line tells us that. If it's negative like it is here, that means when we raise the pressure, we go from solid to liquid. If it was a positive slope, it would be the opposite. It means when we raise the pressure, we go from liquid back into the solid region, and that means the solid is more dense. So you can predict the relative densities of the solid and liquid phases by the slope of that line that divides them. Another point on this diagram here that we haven't talked about yet is the point where all three of these lines intersect each other right there. So it's labeled as O in this diagram. I'll put a big X next to it just so we can see it better. And we call that the triple point. So the triple point is the point at which solid, liquid, and gas all exist together. And it's just one specific temperature and pressure where that's true. So as this diagram tells us, the triple point for water is 4.579 millimeters of mercury, so a pretty low pressure, and close to zero is 0.0098 degrees Celsius. So if we take water at close to 0 degrees Celsius and we lower the pressure all the way to 4.5 torr, we'll get to a point where the solid, liquid, and gas all exist together at that temperature. So under these conditions, what it means is that the solid and liquid have the same vapor pressure. But again, the more useful way to think about it is just that all three of those phases exist together at that temperature and pressure. That's what the triple point tells us. So it's the point where all three of those lines intersect would be the triple point. The other point that we have in this diagram here, we'll notice that the liquid gas line, at some point it just ends. And that's not because when we make these diagrams we just get tired of drawing that line and stop. There's actually a reason for that. So the end of this liquid gas line here, which I'll label with a Y to keep it clear here in the definitions, is called the critical point. So when you get to this point here, which again for water is well beyond 100 degrees Celsius and well beyond 1 atmosphere, so pretty high temperature and pressure for that, but this is the point at which the vapor can no longer be liquefied. And usually the way that this is thought of is that once you get beyond this temperature and pressure, so this temperature in this pressure. As you keep going up into this higher quadrant here, beyond the critical point, it basically means that the liquid and the gas phase are no longer distinguishable from each other. You don't have separate liquid and separate gas phases. It's just one phase that we call a supercritical fluid, where it's it's not a separate state of matter, but it's just at this point you can no longer distinguish liquid from gas. So supercritical fluids have pretty interesting behaviors. We're not going to talk about that in this class, but once you get beyond the critical point, the liquid and gas phases are indistinguishable and they exist as this supercritical fluid. We don't really need to know all the implications of that. We just need to know how to identify it on a phase diagram. That point where the liquid gas line ends is called the critical point. And so beyond that point, they exist as a supercritical fluid. Beyond the critical point, it's called supercritical. All right, so that's another couple points in the diagram that we haven't talked about yet. Specifically triple point and critical point you should be able to identify. All right, let's give another example of a phase diagram that just shows one additional feature that we haven't seen before. And so the first thing we'll notice with carbon dioxide here, so this is CO2, and this is going to be solid all the way on the left, liquid in the middle, and then gas over here. What we also see as an interesting feature on this diagram is that if we're at 1 bar of pressure, which is basically 1 atmosphere, bar and atmosphere are almost the same in terms of the unit. If we're at 1 atmosphere of pressure, if we go to, we're in the solid phase here, if we get to minus 78.5 degrees Celsius, we see that we go directly from solid to gas. We don't go through the liquid phase at that pressure and that temperature. So when you go through directly from solid to gas, that's called sublimation. So that's another type of phase change that you can sometimes see. And so sublimation is the process of converting a solid directly to a gas. And carbon dioxide is a classic example of a substance that does this. You've probably heard of dry ice before. That's exactly what dry ice is. It's frozen carbon dioxide, and when it gets to that minus 78.5 degrees Celsius and it warms up, you don't make liquid carbon dioxide, you go directly back to gas phase carbon dioxide. So that's called sublimation, the process of converting a solid directly to a gas. So we see that for CO2 at 1 atmosphere, it's going to sublime at minus 78 degrees Celsius. So most substances can sublime if you go to really low pressures, but CO2 is a rare example of a substance that even at atmospheric pressure is going to sublime rather than melt. So you wouldn't see at 1 atmosphere, you wouldn't see carbon dioxide melting. It would go straight from solid to gas. It would sublime. And so this line between the solid and gas phases, which again, every substance or almost every substance has this line shown. It's just depending on what pressure it is, you may not observe it at atmospheric pressure, but this solid gas line is where the sublimation would happen. So that's another phase change that we can read off of these diagrams directly from solid to gas. Now the other thing that we'll point out about this diagram is, unlike water, we see that our solid liquid line in this case has a positive slope, which means that if we start in the liquid phase and raise the pressure, we're going to cross over into the solid phase, telling us that for this substance, which is the more typical situation, we have a more dense solid than liquid. So our solid liquid line has a positive slope in CO2. And that means in this substance, the solid is more dense than the liquid. Because as we raise the pressure of the liquid phase, we're going to cross over into the solid phase. And so solid is more dense than liquid. As we increase the density, we're going to convert from liquid back to solid. All right, so that's another feature. Again, we read that off of water, and it's just the opposite here, more typical situation of it being positive. All right, the last phase diagram I'll give you before going through a bunch of example problems is that for the element carbon. So in carbon here, this is the first example of one where we really have two different solid phases. So normally on the left side of the diagram, that's where the solid phases occur, but we see that there's this extra line here, and really there's now 4 regions in this diagram instead of 3. Now you wouldn't be able to easily predict this off the top of your head, but we can still predict that this is liquid because it's sort of the middle part. This is gas over here. But then there's 2 different solid phases. Now you guys know what these are called for carbon because you've surely heard of these. So this one is called graphite. And then at much higher pressures, it exists as diamond. All right. And so that's just an example of a phase diagram that has 2 solid phases, just to be aware that that's a possibility. You wouldn't have to know which of these is diamond, which is graphite. We're not expecting you to know that kind of level of detail, but just be aware that 2 solid phases or more than 2 solid phases is possible. Now what we also notice is that if we start with diamond at very high pressure, this is 10 to the 11th pascals, 10 to the 5th pascals is about where we exist on Earth. So this is several orders of magnitude higher than the pressure that's around us right now. So if we cool back down, or not cool back down, if we lower the pressure back down to regular pressure, then graphite is going to be formed instead. So diamond is going to convert to graphite. So we notice that at high pressure, about 10 to the 9 pascals, graphite will convert to diamond, but if we let the pressure drop back down, the opposite will happen. So probably in my opinion, the most egregious example of false advertising that's out there is all the diamond companies that say a diamond is forever, because that's wrong. Because if you let a diamond sit there, it's going to convert back into graphite. Now the reality is that takes a really, really long time, millions of years probably. So on the human time scale, it's fine. But diamond is not the most stable form of carbon, and when we're at normal conditions on Earth, graphite's the most stable. So over some really long period of time, that precious diamond that you have will convert back into graphite, which, as you know, is like a black flaky substance that would fall apart. So that wouldn't look so nice as a piece of jewelry. So the phase diagram tells us that, and again, the main point of this was just to show you an example of one that has different solid phases being shown in the same diagram, which for a lot of different substances can be the case. All right, the last thing we'll do, I don't know if we'll get through all of them, but most of them anyways, just some quick example problems, just the kind of things that we expect you guys to be able to know about phase diagrams. So just when you get to the homework problems, there won't be any huge surprises. We don't expect you to know these in a lot of level of depth, but just to give you an example. Okay, so for this substance here, what phase or phases are present at point A? Okay, so we have different points in the diagram labeled. So to identify this, we have to know that, again, all the way to the left is solid, middle is liquid, all the way to the right is gas. So those are the 3 main regions. Point A is not on the boundary between 2 phases, so that means there's only going to be 1 phase existing there, and it's only going to be solid. Okay, so if you're in a portion of the diagram where you're not along one of the boundaries between phases, then you only have that phase present that is indicated by where you are in the diagram, in this case solid. Okay, so that one was fairly straightforward. If we go to point B now, same diagram, but now we're talking about point B here, what are the phase or phases that are present here? Again, same regions, solid, liquid, gas. But this time we're on a boundary line between 2 of them. This is, in this case, liquid and gas. So at that point there, both liquid and gas would exist. Whenever you're on the phase change line between 2 different phases of the diagram, both of those phases exist under that condition. And so you have at point B, liquid and gas coexisting together. All right, so when we ask you about these diagrams, which phase or phases exist, you just have to look at, are you in a region of the diagram where only a single phase exists, or are you on the boundary line between 2 or more phases, in some cases all 3 if you're at the triple point. All right, so that was one example. And then we have which temperature and pressure are closest to the triple point. So if we ask you to identify the triple point in a diagram, that's where all 3 of the lines come together, the solid, liquid, and liquid gas and solid gas lines. So all 3 of those lines come together right there, that intersection point, and we just want to know which temperature and pressure give that the best. So if we go down to the x-axis, that gives us the temperature. Temperature is around 120 Kelvin. We have to estimate because we're in between 2 numbers, but it's around 120. And then the pressure, we're right at 0.6 atmospheres. So we go over the y-axis to find pressure, which is in atmospheres in this diagram. So 120 Kelvin, 0.6 atmospheres gives us the triple point. That would be A there. Okay, so 0 Kelvin doesn't even show up on this diagram, or if it does, it's like way at the origin. 110 would be, and 1 atmosphere would be at point A there. 290 is way past triple point. So the triple point is right there where they all three come together. All right, any questions so far as we just quickly go through these? I think we can probably get them done. All right, for this one here, we want to know, same exact diagram, we're just asking all these different things about it. What are the normal melting and boiling points? Okay, so remember that the normal melting point and boiling point occur at 1 atmosphere. Melting is the temperature at which you go from solid to liquid, and then boiling is the temperature at which you go from liquid to gas at that pressure. So the way we're going to do this is we're going to find the pressure we're looking for, which for the normal melting point and boiling points is 1 atmosphere, and we're just going to go over until we get to there. That's where the solid and liquid intersect, so that's going to be our melting temperature. So if we go down to the x-axis at that point, that's going to give us the melting point. So we'll call this here point X, which is the melting point. And when we extrapolate down to the x-axis, it's, again, we have to estimate a little bit, but it's around 110 Kelvin. There's going to be a little bit of estimation that goes into these diagrams. So if you're doing a multiple choice question especially, just pick the answer that's closest, because you have to use your eyeballs, and there's a little bit of, if you might want to use like your scrap paper to like kind of hold it up on the screen and kind of line it up everything as best as you can, but just pick the answer that's closest, because there is going to be a little bit of estimation that goes into some of these. But then to find the boiling point, we keep going at 1 atmosphere until we get to the liquid gas line. So that's the liquid gas line there. That's where they intersect, and we go down to the temperature to find where that occurs, which is about 220 Kelvin. Again, a little bit of estimation that has to go into this. So point Y here is the boiling point, which is going to be approximately 220 Kelvin, about as precise as we can get on this diagram. But that's the temperature where we get the liquid gas equilibrium. All right, are we out of time? Yes. All right, I'll just save the last 3 for next time so we can try to retain some of this information and just review it, and then we'll move into the second half of this chapter, which deals with solids.